In this chapter, we are going to examine bonds that have embedded options. So the highlights of this chapter are first, which bonds have embedded options in them. And in particular, we're going to be talking a lot about callable bonds. Also, we're going to be talking about puttable bonds, but mainly about callable bonds. Then we're going to see one of the main features of callable bonds is that they have a different convexity than non-callable bonds or plain vanilla bonds. And finally, we're going to talk about the optimal call policy on these callable bonds. Let's see some examples of options embedded in bonds. So a first example are convertible bonds. So convertible bonds are bonds that, depending on their price, can be exchanged for stock. A second one are callable bonds. So callable bonds are rebought early by the issuer. That means the issuer sells the bond to the market and then at some future date says, you know what, I have this option to buy back my bonds, and then they buy them back. When would you do that? Well, if you're doing too well, hence your interest rate is really low, then you say, I'd rather have those bonds back. And the third option are puttable bonds. So puttable bonds, it's the opposite than callable bonds. So puttable bonds are going to give the bondholder the chance to return the bond to the issuer. So it's like the bond is doing so bad that you don't want to have that bond anymore, so you decide to give it back to the issuer. Let's see some characteristics of callable bonds. The call provision allows the borrower, that means the person selling you the bond, to buy it back at some predetermined price. And usually this price is above the face value. Now that call price can vary over time and it usually declines. Finally, there's something called the call protection period. This call protection period is a clause that protects the bond from being bought back by the issuer before a certain time. Let's give some examples. So let's see a callable bond example. So let's imagine that you have a 10-year callable bond and that this bond cannot be called before year 5. Now, in the future, after year 5, the issuer can buy back the bond at certain prices. Like in year 5, it can buy it back at a price of 107.5. At year 6, at a price of, again, 107.5. Year 7, 106. Year 8, 106. Year 9, 103. Now, notice that the prices of these bonds are decreasing as they approach maturity. Another characteristic of this callable bond is that the callable bond is equal to the plain vanilla bond minus a call option. The call option is basically this buyback that the issuer can have on the bond. So it's like you are selling a call option to the issuer. So then for this reason, a callable bond is going to have higher yield than plain vanilla bond. When we talk about callable bonds, we need to talk about two concepts that are the yield call and the yield to worst. The yield to call is something that is going to be computed just exactly in the same manner that the yield to maturity, but is going to assume that the bond is called. The yield to worst is going to be the minimum of all the yields to call. So there's going to be several of them depending on the number of callable dates there are, and the yield to maturity. And this yield to call and yield to worst is going to have the same problems that we know the yield to maturity has. Let's see some examples. Let's see an example to further understand the concepts of yield to call and yield to worst. So we have a 10-year bond that has a coupon of 5% per year and a par value of 100. Now we're going to set the price to 100, and this is going to imply that the yield to maturity of this bond is going to be equal to 5%. Why? Because when the price is equal to the face value, then the yield to maturity is going to be equal to the coupon. This bond is going to have a couple feature, and it can be called in years 6, 7, 8, and 9. And then the price at which it can be called is 120 in year 6, 117 year 7, 114 year 8, and 111 year 9. Now, let's examine the case of year 8. So this bond in year 8 would look as follows. Since it's going to be called, then the buyer of the bond is only going to receive coupons from year 1 to 8, and then in year 8 he's also going to receive the par value. And the coupons he's going to receive from year 1, 2, 3 up to 8 are $5. The yield to call is computed assuming that today you would receive 114. which is the price at which it's going to be called. So here you would compute the yield to maturity of this bond here, and that yield to maturity is not the real yield to maturity because you have certain assumptions here. So it's called the yield to call. So the yield to maturity is computed as follows. Like you said, the price equal to 5 over 1 plus y, and discount all the coupons. And then the last payment it's made in year 8. And then here you're going to solve for y. And then you're going to find that y is equal to 3.01%. So this is going to be the yield to call. For the other maturities, if we apply the same methodology, the yield to call that we're going to find are 1.49% for year 6, 2.34% for year 7, 3.01 for the year 8, and 3.55 for year 9. Then the yield to worst is going to be the smallest yield among yield to maturity of 5% and all this yield to call. So then the yield to worst is going to be equal to 1.49%. But then the next question is, why would an issuer include these callable features in his bonds? The reason is as follows. When you issued the bond, you're paying a coupon of 5%. And then the yield to maturity was also 5% since it was issued at par value. 8 years go by, let's say, in our example, you go and check what your yield to maturity is going to be. And then the yield to maturity, let's say it went down to 3%. So then if at this point in time you decide, okay, I'm going to issue new bonds, you're going to issue them at par value, then the coupon in this bond is going to be 3%. So this means that if you call your bonds, you're going to pay the 114, but then you're going to be able to issue new bonds at par value. And instead of paying the 5% coupon, you're going to start paying 3% coupon. Another way of seeing this problem is that your company did so well that the bond prices went up, the yield to maturity went down, hence your borrowing costs are now much lower than what they were before. I mean, if we see this problem from the perspective of the firm, I would pay a coupon of 3% instead of a coupon of 5%. Now let's see that problem of the callable bond in a graph. So we know that the bond was issued at a yield of 5%. And then at that yield, the price was 100. Now, if the yield goes down, let's say to 3%, then the bond is going to have a certain price, like 114. The yield goes from 5% to 3%. So then in that case, the price would go to 114. Now, what happens? Can it go to 2%? At that yield, the price was, let's say, 120. Now, the thing is, because the bond can be called, then you're going to have that this is the price of your plain vanilla bond, and the price of your callable bond is going to be bounded by the 114. It cannot go further down than that. So you know that as the yield starts to go down, then you're going to have this graph that is going to go like tangent to your 114. As you can see from here, the price has a negative convexity. What does that mean? Normally the bond prices have a positive convexity, but in this case, because the price cannot go above 114. And why can it go above 114? Because everybody knows that the bond is going to be called if it goes below 114. So the callable bond is not going to go below the price at which it's going to be called. Hence, there is this negative convexity. So basically, you have that one looks like this, and then the other one would look like this. So this is the price of your callable bond. So as we just saw, the convexity of callable bonds says that for a plain vanilla bond, they have positive convexity, but for callable bonds, they have negative convexity. Why do they have negative convexity? Because as the rate gets lower and lower, they're more likely to be called. Now, this negative convexity has some important consequences. The first one is that you need to take into account when you're hedging. Why? Because you don't want to mix portfolios that have positive and negative convexity, because it's going to make your hedge unstable. So when you issue callable bonds, it's going to be interesting if your assets have negative convexity. And an example would be Fannie Mae that owns mortgages. So if you own mortgage, your mortgage has this prepayment option, and this prepayment option generates negative convexity. For example, it's a fact that in Mexico, mortgages are paid in about 7 years. That means mortgages that should last for 15 years, 20 years, and so on. People pay them really, really fast. Why? Well, because of this prepayment option. So that means that a bank is subject to this negative convexity. So if you decide to go and hedge your portfolio, you better do it with an asset that also has negative convexity to make your hedge stable. So we saw that callable bonds is basically a plain vanilla bond minus a call option. So this call option is what is that short position that you gave to the issuer of the bond so that he can call the bond. Callable bonds, usually they pay higher coupons. So in principle, given these two bonds, the callable bond should have a lower price than the plain vanilla bond, since you're subtracting the value of a call option. What they do instead of making them have a lower price is that they make them pay a higher coupon so that they look more attractive to the public. Now let's examine the case of puttable bonds. If for callable bonds, you're expecting that the company is going to do better, then as an issuer, you want to buy back the bonds from the buyer. In the case of puttable bonds, is the opposite. It is that you're selling an option to the buyer of the bond so that if the company does really bad, he can return those bonds to you. So let's imagine that it's just like in the previous case where the yield to maturity was equal to 5, it paid $5 coupon, and now the maturities for are 6, 7, 8, and 9, where the price can be sold back to the issuer, and the prices are 80, 83, 86, 89. And then, just like we did before, we're going to compute the yield to put. It's going to be 9.53, 830, 730, and 666. Let's examine the case of the 8-year maturity with a price to be sold back to the issuer of $86. So in this case, what's going to happen is the bonds of the company started with a price of 100, and then they went down to a price of 86. That means that the company is doing really bad. The company is doing worse than what they expected. But let's imagine that this price is going further down and they go down to 80. So if they go so much down to 80, so at that point in time, the buyer of the bond has the option of returning back the bond to the issuer. The issuer is going to pay $86 to him instead of what they're worth in the market, which is 80. Hence, he's going to be making like $6. Now, the next thing he's going to do is the following. With this bond was paying a coupon of 5%. So what he could do instead is take his money and buy some new bonds, maybe of a similar company, that would actually be paying a coupon of 7.38%, because this would be the yield to maturity. So if the bonds are issued at par, if the par value is equal to 100, then the coupon of these new bonds would be 7.38. So that means that he would be making some extra money for buying those new bonds that are issued at this yield to maturity, or at this coupon of 7.38. One final remark, puttable bonds is then equal to a regular bond plus a put option. So in this case, the puttable bond is going to be more expensive than the regular bond. Why? Because you are the holder of a put option. Why? Because you can sell back the bond to the issuer given certain conditions. So what's the optimal call policy for the issuer of the bond? First, the embedded option that you have, the call option, is going to be a European option during the call protection period. In our example, it was like for 5 years. And then it's going to become an American option afterwards. Now note that this American option is going to have different strike prices. So the different strike prices, they're going to depend on each of the call option prices. What's the objective of the issuer? His objective is to minimize the market value of the bonds. He wants to pay the least possible for the bond. So he wants to maximize the value of the call option. How does he do that? Well, he treats his options like American calls, and then he exercises the option as soon as the market value of the bond exceeds the call price. So let's consider an example to further understand how this works. So we're going to have a binomial Vasicek model with local expectation hypothesis. T is going to be equal to 4 years. M is going to be equal to 4, mu 7%, sigma 2%, the mean reversion parameter 0.6. We're going to start with a short rate of 9% in continuous compounding, and then we're going to have a coupon bond with maturity in year 4. The face value is $1,000, and the annual coupon is $130. And then we're going to analyze the two cases, the cases of the non-callable bond and the case of the callable bond. So this would be the evolution of the short rate. This is done with 1 year compounding. We have here the probabilities, and here we have like the up rate, the down rate, and so on. You see that there's some branches of the tree that are not here, and this is because the probability became 0 when we went up here. And same thing when we went from here up. Now I create the discount function for all the branches. So here the way to read this is 0d1 is equal to this, 0d2, and so on. And this one would be 1d2, and this one 2d3, 3d4, and 4d5. So this is year 0, 1, 2, 3, and 4. So now we can compute the value of the non-callable bond. This is what I'm going to call the X coupon prices, meaning that, for example, at maturity, you're going to receive the price of the bond, the face value, plus the coupon, but these ones are before coupon. So you're going to receive basically 1,000 before coupon. In a second, we are going to see why. So now let's derive this price, the 1053.83. To derive the 1053.83, we need to take into account that we have cash flow at time 3 and then at time 4. So at time 4, what are we going to receive? We're going to receive the face value, the 1,000, but we're also going to receive the coupon. So we're going to receive 1130. And then what they're asking us is what's the price here. So the price of the bond would be the 3d4 times 1130. And this is the same thing then, 0.9326 times 1130. And this gives us the 1053.83. Let's give another example. Year 1 at t equals 1. We have that the price of 1151.17 is equal to 1130 times 0.8114 plus 130 times 0.8698 and 130 times 0.9326. Finally, you can also compute the price at t equals 0. I'm going to put it in terms of discount factors. So this would be 1154.14. So in this case, you have to do 1130, 0d4 plus 130 times 0d1 plus 0d2 plus 0d3. You replace by the discount factors, and then you should get this present value. So now that we have derived the prices of the non-callable bond, let's see the case of the callable bond. So the callable bond is a bond that is going to be protected in year 0 and 1. So that means it cannot be called. Now, in year 2, it has a callable price of 1130. And then in year 3, it has a callable price of 1065. Now, if the bond is called, the issuer is going to pay the call price plus the 130 coupon. So now we're going to put the prices that are X coupon. And so these are the prices at which you would buy the bond. When you sell, you would get the price plus the accrued interests. Like in all options, first, we need to check what happens in year 3. So in year 3, the bond can be pulled at a price of 1065. So we go and check what happens in year 3. So the prices are 1012, 1053, and 1097. The price of 1065 means that you can go as the issuer and give 1065 to the buyer of the bond, and he has to give you back the bond. So you would call the bond when the price exceeds your callable price of 1065. Why? Because the market price is 1097 and you can buy the bond for 1065. That means you're going to be saving some money. So when we go and put the price of the callable bond, instead of the 1097, we're going to put the 1065. So here the bond was actually called. Now, since these two prices didn't change, this price is not going to change. Now, this price is going to change. So let's see how do we get this price. We get it by synthetic replication. So let's do synthetic replication with the 1053.83 and the 1065. Now, one little trick you need to remember here is that you need to add the coupon because those are ex-coupon prices, but in year t equals 2, you know that you're going to receive that price plus the coupon. So you need to include those two coupons of 130, and then you're going to replicate with that 1-year bond in that node and the 2-year bond in that node. So this would be the replication for the up and this one for the down scenario. And then we're going to solve for N1 and N2. We're going to find that N1 is equal to 913.75 and N2 is 289.61. Then the call price is going to be equal to your discount factor times N1 plus 0.8964 times N2. And we get that the callable price is 1129.15. So this bond is now 1129.15. If you look at the bond price before, for the non-callable price, it was 1136.59. So in that case, you would have said, oh, the call price in year 2 is 1130. So if you don't compute the proper price, you would have gone here and say, oh, it should be called. But no, that's not the case, because first, since you called it here, you paid a lower price. That means that overall this price is going to be lower. And after computing it from synthetic replication, we realize that yes, it's lower. It's 1129.15. So now we have to do again synthetic replication to get this price and to get this one. Now, a trick that we can use here, because this tree was constructed under local expectation hypothesis, is that we can use the discounted price times the expectation. So this would be the discounting factor, and then the expectation is going to be the probability of the up move, so the 1072.5. Now you would have to add coupon and then the probability of going down times the price plus the coupon. So in this case, you're going to have the 1147.72. You can use exactly the same trick for this one, for the 1151.77. So this one is going to be equal to 0D1, and then probabilities, the probability of going down is 0.25, and then it's going to be 1147.72 plus the coupon, because you're going to receive that coupon in that year, plus 0.75 times, actually this is 1075, this is 0.75, this is 0.25, this is 1077.01 plus 130. So actually this trick, you can only use it when we're under local expectation hypothesis. Otherwise, you must do synthetic replication. Now, we still have one question to answer, which is, what is the call option price? So the call option price, in principle, you would say, oh, I have to go and compute now all my calls and so on. Trick is, since we know that the callable bond is the non-callable minus the call, here we can write that the call option is the non-callable minus the callable. So we basically subtract these two trees, the non-callable from the callable, and then we're going to find this tree. So that means that the embedded option that you have in the callable bond is worth 2.37. And here is where you exercised that option. Conclusion of this chapter, we saw options embedded in bonds. In particular, we saw callable and puttable bonds. We talked about the convexity of callable bonds, and we saw examples of how to price callable bonds. Thanks for watching.